Okay, so for number one, what kind of question is that? It's what? Okay, it's a work energy theorem question where potential energy is being changed because they're asking of us about height and they're telling us how much work is done. If they give us how much work is done, does that actually save us work? Yeah, because now we don't have to do force times distance. It's already done for us. Okay, they told us 183 joules. Is it similar to number two? Yes. Instead of saying how far does this force act over or what is this force, they just ask us to find what's the work. Okay, how much work is done, which is, again, saving us some time. We have less manipulating to do. All right, so let's have a look at number one here. So for number one, we got first off that work's a change in energy. Okay, we know that energy is changing. In particular, it's potential energy because the box is being lifted from the ground, okay, to a height of 1 point. That's a different question. Let's just look at this one. Okay, so we've got still a change. Work is being a change in potential energy. That's an A, not a triangle. Okay, work is a change in potential energy. All right, how high does the box get? Okay, well, it's lifted from ground level. How much energy does it have there? 0. So can I say then that work is going to be equal to the final potential energy minus 0? Is that true? Yes. There's no sense writing that then. Okay, I can simply do this. Work is equal to m times g times hf. The final energy is the change in energy because there wasn't any to start with. No. I'm just doing that because I'm kind of walking through every step. No, on an exam, I would not expect you to write down minus 0. You could if you wanted to. For me, it's just kind of a matter of following the steps and working it out in my mind. Okay. All right. So we plug in our numbers here. We got 8.5. Yeah. Sorry. We got to manipulate for h. Sorry. We got. How do we get hf by itself? Divide both sides by mg. Okay. So we're going to be left with 183 joules divided by 8.5 times 9.81. All right. So 183 divided by 8.5 times 9.81. Whoop, I missed the 0.5 there. All right, so it's going to get lifted to 2.19 meters. Okay. No, HF, final height. Final height, yeah. Sorry, it's supposed to be subscript. I know it's kind of big, yeah. Okay, any other questions on number one? Okay. For number two, okay, we got a soccer ball that has a mass of 0.75 kilograms and it's kicked from rest to a speed of 21 meters per second. How much work is done? All right, well, if they're asking me how much work is done, I know it's this kind of a question, okay, that work's a change in energy as soon as work is mentioned. What kind of energy is being changed in this one? Kinetic, because they're talking about speeds, okay? It's kicked from rest. How much initial kinetic energy does it have? 0. All right, so are we pretty much in the same boat as last time, except instead of mgh, it's 1/2 mv squared. Right? I mean, I could put the minus 0 there, but as I said, it's not really necessary. We know it's 0, and subtracting 0 doesn't change any numbers. All right. Do I have to manipulate? No, it's asking me for work. The final kinetic energy is the work because it didn't have any at the beginning. All right, so all we got to do is plug in the numbers. 1/2 times 0.75 times 21 squared. All right, so 165.38 joules worth of work. Okay, those making sense? All right, those are pretty basic. All right, I would expect that on an exam, you would have a force times distance operation on the other side rather than just being asked to calculate work. All right, so more like the examples we did in class. All right. Okay, I need you to take out your notes package. Lesson 14, conservation of energy. Looks like this. So the first part of this is going to be review of work energy theorem a little bit. Okay? But then we're going to start looking at this whole energy can't be created and it can't be destroyed thing. Yeah, I don't pay the power bill here. Go ahead and plug it in. All right. So the first sentence here, this one, okay, when energy is transferred to an object, it can cause a change in both kinetic and potential energy simultaneously. We don't deal with any questions where that actually happens, okay, in Science 10, but it's important to know that that's true, because it's one of the first things we do with energy in Physics 20. That first sentence is really a restatement of what? No, not the law of conservation of matter, nor is it the law of conservation of energy. It's sort of the law of conservation of energy, but really it's more back to this. Right? If energy is transferred to an object, transfer of energy is work. Okay? It can change both the kinetic and the potential energy of the object, that is, the mechanical energy of the object, easily. Okay? It could change both kinetic and potential because it can change the mechanical energy of an object. We've got to remember that work is a change in mechanical energy. All right? Is that ringing a bell for everybody? Yeah? Okay. All right, so if I throw a ball upward in the air, okay, it has kinetic energy because of its motion, but it also has potential energy because it's above the surface of the Earth. Okay? And kinetic and potential energy are closely related. That's why they add up to essentially a single total. Okay? Mechanical energy. Mechanical energy is the sum of how much kinetic and potential you have. I don't know why I wrote that, it's right here, but anyway. If I throw something up in the air, what does it do? It comes back down. Okay. Why does it come back down? Because of gravity. Okay. So when it leaves my hand, the only force acting on it is gravity. Okay? Because I'm not pushing on it anymore. Whatever, I did some work on it, I threw it into the air, but once it leaves my hand, it's got all the mechanical energy it can ever have, at least for this part of the time. Okay? So as it travels upwards, it slows down. If you're slowing down, you're losing what kind of energy? Kinetic. Are you losing mechanical energy? No. Okay? You're not losing mechanical energy because you're not doing any what? You're not doing any work. Okay? As this thing flies up in the air, it's not doing work on anything. It isn't transferring energy to anything. Then how can it lose kinetic energy? If it's losing energy, that energy has to go somewhere. Exactly. It's turning into potential energy. It's slowing down, but it's going higher. So as kinetic energy decreases, potential energy increases until it gets to a stop at a maximum height. Okay? At our maximum height, we have no kinetic energy because that's the moment where, that instant in time where the object isn't moving, because it's going to turn around and start coming back down. Right? So when it leaves my hand, it has the most kinetic energy it can have. When it's at its highest point, it has the most potential energy it can have. And then as it falls back down, that potential turns back into kinetic. Right? When it comes back to my hand, if my hand is at the same height it was when I threw it, it's going to have the same amount of what? Mechanical energy. Right? Okay? When it leaves my hand, let's say I do 200 joules worth of work. When it leaves my hand, it has how much energy? 200 joules. When it reaches the top, its maximum height, it has 200 joules. When it comes back to my hand, it has 200 joules. Okay? Energy can't be created, it can't be destroyed, but it can be converted into all different kinds of energy. Okay, we're going to deal with the simplest situation where kinetic turns into potential and potential turns into kinetic. That's the law of conservation of energy. Okay, the total amount of mechanical energy stays the same, right? But the amount of kinetic and the amount of potential changes. Okay, no, you got it? All right, so let's look at this first example here with the baseball thrown in a straight line through the air, so horizontally, which is physically impossible, but we'll pretend it's not. Okay, why is it physically impossible to throw something in a straight line? Because of gravity, right? It always arcs down. We're going to assume. Okay, all right. So a 0.3 kilogram baseball is thrown in a straight line through the air. Okay, at a height of 2.5 meters above the surface of the Earth, it has a speed of 20 meters per second. What kind or kinds of energy does it have? Both, right? It has some potential because it's 2.5 meters off the ground. It has some kinetic because it's moving at 20 meters per second. Can I calculate how much of each? Yes, because I also know the mass. Okay, if I know the mass and the height, the mass and the speed, I can calculate, okay, the two different kinds of energy because I always know what G is. All right, so that's what they're looking at here. Okay, if I want to find the total mechanical energy of the baseball, that's the kinetic energy plus the potential energy. Okay, the formula for kinetic is 1/2 mv squared. Formula for potential, m times g times h. Plug in our numbers. 1/2 times 0.3 times 20 squared plus 0.3 times 9.81 times 2.5 meters. Okay, so 60 joules of kinetic, 7.36 joules of potential, 67.4 joules of mechanical energy. Okay, now that ball, let's say that that's the instant I throw it. Okay, that's how much mechanical energy it has the instant I throw it. If there's no air resistance, the ball is still going to do this. Okay, and it's going to arc down to the ground. How much energy will it have here? Mechanical energy will it have there? 67.4. What's going to be different there? Right. Okay. There's going to be less potential, but there's going to be more kinetic because it's accelerating down to the Earth. Okay. So it's going to speed up, but it's going to get lower. Okay. The potential is going to turn into kinetic, but they're still going to add up to 67.4. And that's true here the instant it hits the ground as well. Okay. Is that making sense to everybody? Okay. Among other reasons, this is one of the reasons why you're not allowed to discharge firearms within city limits. Okay? Even if you were to just fire a gun into the air, which seems harmless enough, okay? The bullet leaves the gun with a certain amount of mechanical energy. As it travels upwards, that kinetic energy becomes potential, and then it begins to do what? It needs to come back down. Now, in the real world, this doesn't hold true. It's not going to have the same amount of energy when it comes back down because the bullet wouldn't fall in its most aerodynamic dimension on the way down. It'll actually tumble. Okay, so you could almost catch it if you knew where it was coming. Okay, but in the perfect physical world, by the time it got back down to the level it was fired, it would be going the same speed it was fired at. That would be dangerous. Okay, so it would be like if you threw a big shot put right straight up in the air. You wouldn't stand there and wait for it to come back down. You get out the way, right? Because you know when it comes back down, it's going to have a lot of energy, okay? The same amount as you put work into it, okay? When you threw it up in the air. Everyone follow? All right. Question. Shoot a gun, bullet goes this way. Drop a bullet from here. Which one hits the ground first? They're dropped from exactly the same height. Which one hits the ground first? At the exact same time. I don't see anyone's minds blowing. Okay. It's weird though, isn't it? We wouldn't think that that's the case. But what do they have in common? Their height. Okay, their height is the same. The acceleration due to gravity is the same. The distance they have to fall is the same. They'll hit the ground at the same time. Will they hit the ground in the same place? No. Okay, but they'll hit the ground at the same time. All right. This is why marksmanship is such a practiced ability. Okay, you have to, if you're making a long shot, you have to account for the fact that the bullet drops as it travels. Okay? It does this, it arcs back down to the ground. So you have to keep that in mind. If you're trying to hit a very distant target, you actually have to end up aiming way above it to account for the fact that the bullet will drop on its way there. Right? So if you've ever seen any of those kind of sniper movies or anything like that, okay, they make it look really easy, but in actual fact it is very, very difficult to make long shots where the bullet's flight time is several seconds. Okay? Because every second an object is in flight, it falls 4.5 meters. So if your bullet is traveling for 1 second, you have to aim 4.54 meters above the target to account for the drop. Okay? How many people have seen Saving Private Ryan? Okay, there's a scene there where he shoots the guy in the clock tower, right? And he adjusts the scope. I don't know, you may not have paid attention to the detail, but he says it's about 800 yards, maybe a shade under, that's 2 clicks. And he clicks the scope twice, which lowers the scope. So it's aimed, so when he looks through the scope, it's aimed downwards. So to get the target in the sight, he has to aim the barrel upwards. So he has the target in the sight, but the barrel isn't aimed at it. It's aimed above it. Okay? So when he fires the gun, the bullet's drop is accounted for. Okay? Yeah, it's a weird thing. Okay? That's why real special forces snipers have a spotter with them all the time. Okay? The spotter is taking distance readings, wind readings, and all those things and factoring all that in. Okay? They do math on the fly. You want to be a spotter, you got to be good at vectors. Okay? All right, let's try 8, 9, and 10. Okay, one of you guys try 8, 9, and 10. They're just like the baseball question we just did. Okay, calculating essentially the total mechanical energy, okay, of the object, or maybe they give you the total mechanical energy and they ask you to find the potential or the kinetic. Okay, in either case, they're using this formula. Okay, mechanical energy is kinetic plus potential. This is the building block for where we're going with conservation of energy. Okay, give you a couple of minutes to do those. These are the answers, by the way, okay, so you can check them. All right, so one of the tricks right off the bat is checking to see if you remember what units everything needs to be in. If I want to get something in joules, mass needs to be in kilograms. Okay, so obviously we get a really, really big number if we use 300 here. Okay. The other thing we got to remember is that speed has to be squared when we plug it into 1/2 mv squared. Okay, another common mistake. So if we're looking for number 8 here, okay, if we're looking to do number 8, we've got that mechanical energy is kinetic plus potential. Okay, so that means 1/2 mv squared plus m times g times h. So we got 1/2 times 0.3 kilograms times 8 squared plus 0.3 times 9.81 times 30. Okay, so that's the height, 8's the speed. Okay, when we plug that in, all right, we got 0.5 times 0.3 times 64 plus 0.3 times 9.81 times 30. All right, so 97.89 joules. Questions on number 8? How are we doing on number 9? How many people have done number 9? Okay, how many people just need a couple more minutes on number 9? Okay, I'll give you a couple more minutes. Okay, so number 9 is still asking about mechanical energy, except this time it actually gives us the value of the mechanical energy. It says there's 3,000 joules, 3 times 10 to the 3 joules of mechanical energy when the person is clearing the bar. Okay, and while they're clearing the bar, they are still moving at 8.33 meters per second. Right? So do they have both kinetic and potential energy then? Yeah, because if they're clearing the bar, they're obviously not standing on the ground. Okay, so they're at some height. So it's asking us, calculate the potential energy. All right, so they're asking me, calculate this part. So how do I get that by itself? Subtract EK over to the other side, right? Isolate EP. So mechanical energy minus kinetic energy should equal potential energy. I mean, that makes sense. If we add potential and kinetic together to get mechanical, this kind of makes sense. All right, so I know that this is 3,000 joules because the question told me that. Okay, and I know that the mass of the jumper is 55 kilograms, and I know that they were moving at 8.33 meters per second. Right? That should equal my total potential energy. All right, so we got our 3,000, okay, minus 0.5 times 55 times 8.33 squared. All right, so they have 1,091.81 joules worth of energy at the point where they clear the bar. Okay, did everyone follow what I did there? All right, if I was asking this question, I would take it one step farther. Further. Whatever, that's an English thing. Okay, I would ask, how high is the bar? Could I figure that out? What am I looking for? Height, right. I'm looking for h. I still know the mass of the athlete, still 55 kilograms. Okay, I know that their potential energy is 1,091.81 joules. And I know that that equals m times g times h. Can I find out how high the bar is? As long as I divide by mg. Okay, so if I do that, it's going to be 1,091.81 divided by 55 times 9.81. That's impressive. Okay, 2 meters. All right, I've seen the provincial track and field record set many times, and it is just a tiny bit higher than that. Okay, so I think 2.08, okay, for juniors. All right, so that is an impressive high jump. That is taller than me by about that much. All right, that's a pretty impressive high jump. I don't remember off the top of my head. It was just last year. Okay. How many people have done number 10? Okay, can we go over number 10? Yeah? Okay. So is number 10 a lot like number 9? Except now we're looking for kinetic energy. So essentially it's the same thing, right? Okay, I'm solving for EK this time, so I'm not going to subtract EK, I'm going to subtract EP. All right, so we're going to have mechanical energy minus potential energy equals EK. All right, they tell us the mechanical energy is 1,880 joules. Okay, and they tell us the mass and the height. Okay, so that's what we got. The height was 50 meters. All right, so when we plug that in, we have 1,880 minus 2 times 9.81 times 50. All right, so they have 899 joules of kinetic energy. I would again take that question one step further. And that is, I would ask you to calculate how fast the object is going. What is the object here? Oh, it's a hammer. I'd ask you to calculate how fast the hammer is going. Can we do that? Yep, we now just calculated the kinetic energy of the hammer. Okay, EK equals 899 joules, which equals 1/2 mv squared. All right, I know m, so all I have to do is go divide this by 1/2 of m, and then what? Square root. Okay, so we'd have so 899, I need brackets there, brackets. 899 divided by 0.5 times, what was the mass, 2 kilograms? I shouldn't have done that. That's a waste of time. Okay, so 30 meters per second is how fast the hammer is moving. Okay, everyone follow what we did there? Right? That's going to be the expectation here, but there's going to be another step kind of added on to this soon. All right. So, law of conservation of energy tells us that the amount of energy in the system remains constant. It can be converted back and forth between potential and kinetic a bunch of times. The only way a system or an object loses mechanical energy is if it does work. Okay? If it does work, then it's going to transfer away some of its mechanical energy. So, in a true law of conservation of energy question, there will be no work being done. That's how you can identify it as being different from a work energy theorem question. Okay? A work energy theorem question will give you things like force and distance, okay? And it'll probably use the word work, or it'll use transfer of energy or something like that. A conservation of energy question will never give you force, and it'll never use the term work. Okay? Because if there's work being done, energy's not staying the same. It's transferring away to somewhere else. Everyone follow? Okay. All right. The simplest kind of conservation of energy question involves potential just turning into kinetic straight across. Okay? And that's what happens most of the time, but we have to understand that it's not usually that simple. Usually an object has both kinds of energy, okay, when we're talking about different positions. All right, so we'll talk about kind of a really easy one first, okay, and that's this one here. All right, a 1.5 kilogram rock, and it's not in there. All right, okay, so I got a 1.5 kilogram rock that's dropped over the edge of a cliff. Okay, so it's dropped over the edge of the cliff, 30 meters above the surface of the lake. What's the speed of the rock just before it strikes the lake? All right, there's no work being done in this question. So how does the mechanical energy when I drop it relate to the mechanical energy when it hits the lake? They're the same, exactly. Okay, so every law of conservation of energy question starts out like this. The initial mechanical energy equals the final mechanical energy. Okay, it doesn't change. There's no work being done, so there's the same amount start and finish. Okay, now remember, we are dealing with the instant it hits the lake, not after it hits the lake, because after it hits the lake, work is being done. It splashes, it makes sound, it disrupts the water, all that is work. Okay, so we're dealing with the instant that it hits the lake. All right, how do I calculate mechanical energy? We just did a couple examples. Add potential and kinetic. So the initial potential plus the initial kinetic equals the final potential plus the final kinetic. Okay, not saying anything different here. EI still equals EF. Okay, we've just plugged in some of the other energies. Now, at this point, I usually look and see if there's an opportunity to cancel any of those things. Okay, are any of these forms of energy zero? Because then I have less manipulating to do later. All right, I'm dropping the rock. So initially, do I have kinetic and potential or not? No. Which one don't I have? I don't have any kinetic, because if I'm dropping it, it's starting from rest. So I know that my initial kinetic energy is zero. At the end, when the rock hits the lake, do I have both potential and kinetic? No. What don't I have? I don't have any potential, because the lake would be considered to be a height of 0. Okay. Now we have a lot less things to write when we expand out the formulas for EP and EK, agreed? Because we just eliminated 2 of them. So now I'm down to this. M times G times the initial height equals 1/2 mvf squared. Okay? Since there's no kinetic at the beginning and there's no potential at the end, the initial potential and the final kinetic are equal to each other, which is still the same as saying the initial mechanical is equal to the final mechanical. Just some of them were zero. Some of those things were zero. Everyone follow what I'm saying there? Okay. It wants me to calculate the speed of the rock just before it strikes the lake. So what am I looking for here? Looking for this. So what do I need to do to get that by itself? Do I want to divide by half of m? Right. I want to take the half and the m over to this side. What happens when I do that? What's m divided by m? Well, not 0, but they cancel each other out, right? It's the same rock, so this is the same number. Okay, so suddenly things are getting even easier. I've got even less numbers that I have to worry about punching into my calculator. All right, I got to do one more thing. Square root. Okay, so the final speed is the square root of GHI over 1/2. Okay, so when I punch that in or I plug in my numbers, okay, it was a 1.5 kilogram rock, which doesn't matter because I'm not using the mass anyway. Okay, 9.81 times, it was 30 meters, right? Okay, so 9.81 times 30 divided by 0.5 square rooted. All right, so when the rock hits the ground, or the water, sorry, it's going to be moving at 24.26 meters per second. Okay, everybody all right with that one? Okay. Now, the only thing that changes as these become more complex is these would actually have values. Okay, they wouldn't be 0, they would have actual numbers, and then you'd have to move a few more things around. It doesn't really change anything, you just have to move more stuff around. Okay. Now, a pendulum on the clock swings back and forth. Let me get my ghetto physics stuff here. This is what happens when you cut money from education. You get the drawstring from a hoodie and an old roll of electrician's tape. You're getting very sleepy. Yeah. All right, so a pendulum swings back and forth. Okay, to get a pendulum moving, I essentially have to take it away from its lowest point, because if I just leave it here, what's it going to do? Nothing, because it doesn't have any energy, right? It has no mechanical energy. It has no ability to move from this position. So I draw it away. Now what does it have? It has potential, okay? Because it's now a certain height, okay, above its lowest point. So here it has potential energy. When it comes back down to that lowest point, it's going to have only what? Only kinetic, okay? And that's just going to keep converting back and forth, okay? Now, because this isn't a perfect system, it slows down, okay? Now, what we often do, I don't always do it, but I sometimes do it, if I have something big and heavy, is I give you the demonstration of the fact that this is not the perfect world, and that energy is always lost. And we take a big heavy bucket, and we hook it up to something that we can hang it from, and then we put the bucket right here on somebody's forehead. And then we let the bucket go. And the bucket swings out, and it comes back. And no one ever gets hurt. Why? Yeah, because energy is lost. The pivot point and air resistance rob some of the mechanical energy from the pendulum. It comes really close. No one ever gets hurt, except that one kid who stepped forward. Hey, you can't fix stupid. Okay, it's just, yeah. Okay, all right. Is that making sense to everybody? All right. I seem to be missing a bunch of pictures here for some reason. Hang on. All right. So on number 11, water balloon is dropped from a height of 12 meters. Okay, calculate speed of the balloon just before it hits the ground. All right, is there any work being done in this question? Nope. Okay, no energy is being transferred away. Okay, it never mentions forces, it never mentions air resistance, none of that. Okay, so we can assume then that this is true. The initial mechanical energy at the point where it is dropped is equal to the final mechanical energy where it hits the ground. All right, that means EK initial plus EP initial equals EK final plus EP final, because that's how you calculate mechanical energy. This is the final mechanical energy, this is the initial mechanical energy. Are any of those values zero according to the question? Okay, which two are zeros? Not the final kinetic. Final potential is zero, okay, because it's going to hit the ground where the height will be zero, and the initial kinetic because it's being dropped. Okay, so we know those two forms of energy are now equal, so I can go m times g times h initial equals 1/2 mvf squared. I'm trying to solve for this. All right, saying how fast is it going just before it hits the ground. So I'm going to divide both sides by 1/2 of m, which makes m go away. All right, and then I have to square root. So exactly the same as the example we just did. So we'll have 9.81 times 12 divided by 1/2, okay, and that'll give us 15.3 meters per second. Hey, everybody with me there? All right, how are we doing on number 12? Good, okay, go over that one then. Okay, so a 30-kilogram child on a trampoline jumps vertically into the air, okay, at an initial speed of 1.6 meters per second. So we're going to assume that that happens from where? From ground level, okay? We're not measuring that they would have compressed the trampoline. That's where they're getting the energy from, but we're not going to consider that part of it, okay? So they've got some initial kinetic, but they're on the ground, so they don't have any initial potential. We're looking for how high the child will rise. At their maximum height, how fast are they going? 0. That's the trick to this question. Okay? At your maximum height, how high they would rise, that's where you're turning around and your velocity is 0. So when we set this up, okay, same as the other, okay, EI equals EF, EP initial plus EK initial equals EP final plus EK final. Okay? This is 0. That's 0. All right? We're looking for the final height. So we got 1/2 MVI squared equals M times G times HF. What do I have to do? Divide by mg. Okay, the m's cancel. When I plug in, I'm going to have 1/2 times 1.6 squared, okay, divided by 9.81. When I do that, I get 0.13 meters. Not very high, but it's just a little kid. Okay, about that high. All right, is this making some sense? All right, so that's what we're going to be working on probably the rest of the week. Okay, and then probably on Monday, we'll do our energy conversion lab, and we'll have to see where we're at. I'd like to do a unit review on Friday, so you'd have the weekend to start prepping, but we may not be to the point where that'll be effective yet. Okay, so that's where we are. Questions? Okay, good luck on your AP social writing thing. Essay, that's what they're called, essay. Position paper, okay, it's not even an essay. All right.